The exponential distribution models quantities where only the time to the first success is important. The probability of success at any instant is constant. It's worth comparing to the geometric distribution where only the number of trials before the first success is important, and the probability of success on any trial is constant. In other words, the exponential distribution is the continuous analog of the geometric distribution. Some examples include radioactive decay, an atom can't decay twice, and customer arrival times, a customer can't arrive twice. It's often used to model time to failure of a device, since a device can only fail once, even though intuitively the probability of a failure should increase as the device ages. We've found that the cumulative distribution function for the exponential distribution is, while the probability density function is the derivative, and in all cases we want x to be greater than or equal to 0. So let's find the mean of the exponential distribution. So that's going to be the expectation of the x times the probability density, and we'll use integration by parts, which give us and we should evaluate this as an improper integral, giving us, which tells us that the mean of the exponential distribution is 1 over lambda. So suppose a product has a mean life of x months, which is exponentially distributed with a mean of 6 months. Find the probability it will last under 3 months. The mean of an exponential distribution is 1 over lambda, so we know that 1 over lambda is 6, which means that lambda is 1/6. So we can write down our probability density function. The probability that the lifetime is less than or equal to 3 months is going to be the integral from 0 to 3 of our density function, which will be alternatively, we could have used our cumulative distribution function, but we wanted to integrate. Also, we forgot that the CDF existed. Now, the exponential distribution is particularly appropriate for modeling radioactive decay. The half-life, T1/2, corresponds to the time at which half the original amount remains, or rewritten as a probability, which we used in an earlier example to find the rate parameter. But suppose we have an exponential distribution, can we find the half-life? Well, let's hope so, because that's what we're about to try. Suppose the time to failure for a device can be modeled using an exponential distribution with a mean of 6 months. How long will it take for half the devices in operation to fail? This time, since we remember we actually have a cumulative distribution function, we'll go ahead and use it. So we know our rate parameter is going to be 1/6, so our CDF will be, and so we want to solve. Half is the probability. So solving this equation gives us and note that the half-life is actually less than the mean. And this occurs because there will be devices that last an arbitrarily long period of time, which will tend to increase the mean. So now let's suppose we have a product with a mean life of x months, which is exponentially distributed with a mean of 6 months. Find the probability it will last at least 12 months, given that it has lasted at least 6 months. So that's conditional probability. We want to find the probability that x is greater than or equal to 12, given that x is greater than or equal to 6. So our formula tells us, now, since lasting at least 12 months includes lasting at least 6 months, then this compound probability is just x greater than or equal to 12. And so the probability we need is the probability x greater than or equal to 12 divided by probability x greater than or equal to 6. So we'll compute the probability that x is greater than or equal to 12 is the integral from 12 to infinity of our PDF, which will be, And again, we should calculate this as an improper integral, giving us the probability that x is greater than or equal to 6 will be, where we should evaluate this as, forget it, just evaluate it the way you would want to evaluate it. And we find that quotient. Now, notice that the probability that x greater than or equal to 12, given that x is greater than or equal to 6, can be interpreted as the probability the device will last 6 more months, given that it's currently working. But also notice that when we computed these probabilities, we found the conditional probability and the probability that x was greater than or equal to 6, and they were the same. In other words, the probability the device lasts another 6 months is the same as the probability the device lasts the first 6 months. The past history of the device is irrelevant. We'll take a closer look at this next because it leads to an important feature of the exponential distribution.